All right, hello. Today we're going to be talking about absolute extrema and the candidates test. And this is the last lesson in Unit 3 of CalBC. All right, so the applicable theorem here is, it's going to be called the extreme value theorem. Is that a continuous function over a closed interval must take an absolute maximum and an absolute minimum. Where by absolute maximum, we mean the maximum value of y on this closed interval, okay? So for the graph on the far left, I'll, just say that the maximum is pretty clearly happening right there, okay? That is the maximum. As opposed to, a couple of times ago, we talked about a relative maximum or a local minimum. This is the maximum or the minimum. Okay, so where is the minimum happening for the graph on the left? Like what at A? Yeah, A and f of A. Okay, so that's, going to be the minimum value. Okay, and so what you're going to find today, or what we're going to do, is that these extreme values, these absolute maxima and absolute minima, occur either at endpoints of the closed interval or at critical points. Okay, so that's going to be important to what we're going to do next. But let's look at the next graph, the graph in the middle. This one doesn't have an absolute maximum. Why? What's going on here? Yeah, exactly. Like you can't actually achieve that maximum value. But what's going on in terms of the theorem? Like what have I done? It is a closed interval, but it's not continuous. Okay, so this function is not continuous, and therefore, there might not be a maximum because of that lack of continuity. Okay, then the next one on the right, you can see that there's not going to be a maximum and minimum value. Those are open circles. I'm not sure if you can see that on your screen or on your sheet of paper if you're sitting in class. This one has no max and no min. Because, say that the y-coordinate right up here at what looks like the max was 1. And, okay, you say, well, we'll just say that the absolute maximum is 0.999. Well, you could go closer, and you could say, well, no, I mean, f of x does get to 0.99999 if the limit is actually 1. So there's not actually one maximum value. And what's going on here? Okay, yes, not a closed interval. That's the deal. Okay, and no, I think there is. I would say that the minimum on the middle one is here at A and f of A. It's slightly lower than, but if they were the same, they would both be the minimum, right? Because a constant function is continuous on a closed interval, and it's just the maximum and the minimum. Okay. Not a closed interval. Oh, no. Blue. And I'm realizing that, you might be saying there, talking about, what is a closed interval? Well, that would be a valid question. Okay. A closed interval, at least for the purposes of this class, is going to be an interval that contains its endpoints. Now, one thing I will mention, and we'll do an example related to this in a few minutes, the set of real numbers is a closed set. And we're not going to get too much into the topology of the real line in this course, it's like kind of beyond the scope of what we're doing here. But I will say, it kind of does contain its own endpoints because the real number line has no endpoints. So you can't say it doesn't contain its endpoints. So it's close. Okay, we'll get to that. Let's talk about how to actually find these maxima and minima. All right, so the steps we're going to take, and we'll call this the candidates test. Also sometimes known as the closed interval test. Is we're going to start by evaluating the function at the endpoints. Okay, then we're going to, then we're going to evaluate the function at the critical points. And then we're going to just find the maximum and minimum from our list. Whatever we're looking for. Okay, and that, that's pretty much it. Really what we're doing is we're going back to the fact that the absolute maximum or minimum will happen either at an endpoint of the interval you're concerned with or at a critical point. Okay, so let's do an example real quick. All right, so for example, we've got find the maximum and minimum values of f of x equals x to the third minus 12x plus 25 on the interval -5 to 3. Now, the first thing I'm going to point out is, the preposition, the maximum, okay? The maximum, not a relative maximum, or find the location of the relative maximum. No, it's the maximum, okay? So what we're going to do is we're going to do, as I described, we're going to start by evaluating f at the end points. So that's -5 and 3. Okay, so let's just go ahead and do that. Okay, plug in -5. -5 to the third is -125. Then I'm going to add 60 because -12 times -5. So I've got -60. No, -65, right? And then add 25, that's -40. Okay. Then when I plug in 3, I'm going to get 27 minus 36 is -9, plus 25 is 16. Yeah. All right, now we need to find the critical points. Okay, so what we're going to do is we're going to take the derivative. So that's 3x squared minus 12. Okay, critical points, that's where the derivative is either equal to 0 or undefined. And, well, let's see. Undefined seems unlikely in this case. So I'm just going to set it equal to 0 and start solving. Yeah, and so I'll say that the critical points are 2 and -2, which are both in the interval I'm interested in. Okay? So I'm going to plug both of these into f of x, see what comes back. 2 to the third is 8, minus 24. Okay, so 8, or minus 24 plus 25 is like just adding 1. So 8 plus 1 is 9. Okay, save myself some trouble there. -2 is going to be -8 plus 24 is going to be 16, and 25 is positive 41. Okay. So if we're talking about, the maximum, well, you go through your list and you look for the biggest number. We're looking for the values of f of x, not the values of x, right? So we're going to say, what is the biggest value of f of x I see? Maximum value is 41, which happens to be at x equals -2. And if you ask about the minimum, you go through there, and you see that the minimum happens to happen at an endpoint. So that's -40, which happens at x equals -5. And that is really how we are executing the candidates test. In kind of an extreme case, at least with the arithmetic. And this is a particle motion question. A particle S position given by x of t is equal to 2t to the third minus 3t squared plus 2 for -1 is less than or equal to t is less than or equal to 2. Well, I'm just going to highlight that because that is one of the first giveaways that this is going to be a candidates test problem, and they give you a closed interval like that. Okay. When is the particle farthest to the right? Okay, that's the maximum x coordinate, the x value. Okay. Particles sliding along the x-axis. What is the greatest x coordinate it achieves on the closed time interval -1 to 2. Okay, so we're going to do the candidates test. So what we'll do is we will start off by setting up our candidates. Know that our candidates are the endpoints and maybe also the critical points. Okay, so we need to find the derivative of x, which is going to be 6t to the 2 minus 6t to the 1, I guess. Okay. And then I'll start factoring this thing, because it's always going to be defined. There's not going to be any critical points of x where x prime is undefined. Okay, so I'm going to set it equal to 0, factor out a 6t, and I'm left with a t and a -1. So it looks like the critical points are t equals 0 and t equals 1. All right, so now all I have to do is plug in on all of these and find which one is greatest. Okay, well, start with -1. That'll be -2 minus 3 is -5 plus 2 is -3. All right, with 2, I've got 8, 16. Minus 12 is 4 plus 2 is 6. When t is 0, x is 2. And when t is 1, you've got x is. So when the particle is farthest to the right is over here at x equals 6. But if you read the question closely, it's asking when is the particle farthest to the right. Specifically, important part being when, which is going to be a t value. So it's going to be at t equals 2. So you could say something like particles farthest to the right at time t equals 2. And now another thing I'm going to also mention is something about the nature of these critical points. You don't always have to consider all of the critical points. I'm going to go back to the graph of the derivative. Okay, this is going to be a parabola. It's going to have zeros at t equals 0 and t equals 1. And we know since it's got a positive leading coefficient, it's going to kind of look like this. All right, well, we want the relative maximum. So over here at t equals 1, that's a relative minimum. Okay, so a local minimum doesn't even really have a chance to be an absolute maximum because it's the lowest value of x in its neighborhood. Okay, so if you ever see that and you're aware that you're looking at a local minimum and you are trying to absolutely maximize something, you can just disregard t equals 1, right? Because it's not even really a candidate for an absolute maximum. It's a relative minimum. All right, what is the maximum value of -x e to the -x squared? Well, if no interval is given, we got to assume over the set of real numbers. So we won't really have endpoints exactly, but what we can do is we could say x versus, -x e to the -x squared. And for the endpoints, we could consider what happens as x goes to infinity and as x goes to -infinity. Now, as far as the critical points go, this would be a good time to practice our product rule. Right? So the derivative of -x e to the -x squared. I'm going to take the derivative of -x first. That's the easy one. So that'll be -1 times, leave this one the same, plus leave -x the same and take the derivative of e to the -x squared. Well, e to the thing, e to the u, is its own derivative. And the derivative of the inside, -x squared, is going to be -2x. Okay, so this could, definitely stand to be rewritten. -e to the -x squared plus 2x squared e to the -x squared. Right? So if I was interested in whether the derivative was undefined, well, I don't think that's going to happen. Nothing I could plug in for x to make something bad happen. But what I could do is find out where this thing equals 0 by maybe factoring out an e to the -x squared. and that would be, I would be left with a negative 1 plus 2x squared. And that is going to give me a couple of critical points. That'll give me, if this thing here that I'm underlining, if that's equal to 0, the whole thing could equal 0. E to the negative x squared will never equal 0. So this would be where x squared equaled 1 divided by 2. And so that would be x equaling the square root of a half, or maybe x equaling the negative square root of a half. All right. So I'm actually going to start with these limits right here that I'm going to highlight in gray. We'll look at the limit as x approaches infinity and negative infinity of negative x e to the negative x squared. Okay. Well, I think what I'm going to do is I'm going to rewrite negative x e to the negative x squared as a fraction. We'll have negative x on top and e to the x squared on bottom. You can see that as x approaches infinity, this is going to be a bigger on bottom situation. The denominator is heavier. This fraction is going to 0. And you could really say the same thing for as x approaches negative infinity. As x approaches negative infinity, the denominator is still heavier, still going to outweigh the numerator, it's still going to go to 0. These things are going to 0. Then, if I were to look at, say, the square root of a half, well, I would have negative times the square root of a half times e to the negative, well, if I square it, I'll have negative half. Well, this is going to be a negative number, and that's less than 0, so this one is like eliminated from contingent. Okay. So I'm probably going to expect this, whatever the y value or the output value I get when I plug in negative square root of a half, that's going to be the maximum value. Okay, so negative square root, so that's just the positive square root of a half, times e to the negative 1/2. That's a positive number. So, the maximum value is going to be this thing that I've highlighted there. Okay? That's a case of one that has a single maximum value over all real numbers. And if you're interested, you could just graph that function and see what it looks like. I'll tell you, it's not that exciting. All right, now the last example I got for you in this video is that the type of problem that used to be, somewhat common in calculus AB and seems to have kind of like fallen by the wayside. But it's one of those problems that's going to be in every college calculus textbook and probably in every college calculus class, so I might as well show it to you. And I really like this because there's a really good strategy to take when approaching these. Okay? The point on the curve closest to some point. Minimizing the distance, right, is what we're doing. Well, first of all, we're not ready to, look at things implicitly yet, so I'm just going to solve for y. Say y equals 1/2 x squared. And we're looking for the point on the curve nearest to the point where x is 4 and y is 1. Well, what I'm going to do is we are trying to minimize distance, right? So we've got distance equal to the square root of, the old distance formula from Algebra 1. Remember that? Y2 minus y1 squared. Well, y2 is, let's say, 1 minus y1 would be, well, y is 1/2 x squared. Okay. Plus x2 minus x1. Well, that'll be 4 minus x squared. Right? Now you look at, running the candidates test on that, and that looks really unpleasant, right? There's going to be chain rule implications. It's the square root of the sum of two squares. That looks awful. But the trick on this one is that rather than minimizing the distance, you want to minimize the square of the distance. Because at a place where the distance is smallest, the square of the distance will also be smallest. So we're only going to minimize the thing I'm highlighting, the stuff under the radical. right? And this is going to be something that we can do because we are pretty good at algebra, right? And I think the play is to, expand this and then take the derivative and set it equal to 0 and see what comes back. So I'm going to, square both of these binomials. I'm pretty decent at that. So that's going to be 1 minus an x squared plus an x to the 4th over 4. And then we're going to add 16 minus 8x and a plus x squared. Okay, and that's the polynomial that we are trying to minimize. Okay, it won't be too bad. Okay, so this is now equal to 1/4 x to the 4th is the highest power term. Then in terms of x squareds, I've got plus 1 and minus 1. That's convenient. I've got a negative 8x and a plus 16 and a plus 1 is a plus 17. And we know if we're trying to minimize something, the best way to do that is to take the derivative of it and find its zeros. So let's do that. So we take the derivative. And we get 4/4 x to the 3rd minus 8. Oh, and I know where this thing equals 0. This is promising, right? Because this is going to be where x is equal to 2. Okay, so that's a good sign, right? I'm seeing some 2's around here. It's looking to me like it's going to be b, which is where x is 2 and y is 2. Let's just make sure that that works. 2y is 4 equals x squared. Yes, wonderful. Okay, I'm thinking answer choice B. Okay. Now, you probably won't see this type of question again in my class, but if you do get asked to minimize the distance between a point and a curve, remember that you can also minimize the square of the distance. Okay, and I'm pretty sure that's all I'm going to have for you in this video. The thing with the candidates test is it's going to come back repeatedly through different units in this class. When we go to do parametric equations, when we go to do polar curves, there's going to be a lot of this, like, maximum distance from the origin. You go to do the context problems, the rate in, rate out questions. You're dumping some sort of liquid waste into a pond, but it's also simultaneously evaporating or something. That could be the type of thing where we need to use the candidates test to find the maximum amount of something that happens over, some specified interval. But for now, if you